Hello everyone, this is a review of my personal notes for week 1, chapter 3. Remember, you can get the text, this beautifulness, in the week 1 questions thread under the post called My Notes. Okay, this chapter is all about compounds. You don't necessarily need to remember what makes up each compound or how we get from smaller to larger. The big take home is that you start off tiny, you get big, and then we think about what each of these compounds has to do with an organism. What is the effect? So we're going to look at the chemistry and try to think about the biology. And please, when you get a chance, look at all the videos. So a hydrocarbon, whenever you're looking at science, think about the parts of the word. Hydro, hydrogen, carbon, carbon. So these are organic compounds made of hydrogen and carbon. The most simple hydrocarbon is going to be methane. This is produced in natural gas, by prokaryotes in swamps, and through the digestive tracts of grazing animals. Methane is considered one of the causes of global warming, so that's why we really care about methane. Let's scroll down. Functional groups, this is the part of our compound that's actually participating in a chemical reaction. The reason we care is if we mess up the functional group so it can no longer participate in the reaction, this reaction cannot happen. So we want to make sure we keep our functional groups happy, which usually means keeping our environment nice and happy and healthy. A macromolecule, actually let's start here with monomer and work up to macromolecule. So monomer is going to be like a tiny bead on a necklace, right? It's a very small molecule. You string these together and we create a polymer. So if you get a bunch of beads, now you have a polymer. If you have the entire necklace, you've got a macromolecule. Examples of macromolecules are carbohydrates, proteins, nucleic acids. To create these polymers and ultimately macromonomers, what you're going to have to do is get rid of hydrogens because each carbon, if we're talking about hydrocarbons, are going to be surrounded by just hydrogens. If we want to pair it up with another carbon, we have to let go of one dance partner, one hydrogen. And that's why it's called dehydration, because we're going to get rid of a hydrogen. If we're doing the opposite, hydrolysis, we got hydro again, and lys means we're going to break up. So we're going to break up polymers by actually adding in a water. So it says, oh, don't be bonded to that carbon anymore. I want to dance with you. We're going to add on a hydrogen and let go of carbon. One example, like they talked about, carbohydrates. Now we think of carbohydrates a lot when we're trying to eat healthier. Carbohydrates are sugars or sugar polymers that can be dissolved in soft drinks. They're hydrophilic. We're going to get to philic later, but that means water-loving, so you can dissolve them. And for animals, they are a source of dietary energy. For plants, they are the material used to give the strength to the plant body. The reason we as animals don't want to eat too many is we do not use the energy from the hydrocarbon. It gets stored as fat. Okay? So if we're talking about sugars, which we are, so this monomer version is going to be a monosaccharide. This is a simple sugar that cannot be broken down by adding any more waters. You're at the most basic. Examples of this is glucose, which is found in sports drinks, and also what our body uses to energize most of the various reactions in it. And also fructose, which is found in fruit. Disaccharide. It's got di, so it means there's two of them. It's a double sugar. So you take two monosaccharides, two one sugars, and put them together, you get a disaccharide. These are found in things like maltose, sucrose, milk sugar. Polysaccharides. This means there's a lot of these monomers together now. These are long chains of sugar units. And an example is starch. Remember, starch is found in plants. We call starches like potatoes, pasta, all the good stuff. And that starch is what gives the plant strength. Animals ourselves, if we don't use all our excess sugar, we're going to store them in a polysaccharide called glycogen. That's just a little note. For cellulose, this is the most abundant organic compound on Earth because It is what forms the tough walls that enclose plant cells. Our plants do not have a skeleton, so they have to use these polysaccharides to create their strength. And we've got a lot of plants out there, so that's a lot of cellulose. So back to our hydrophobic and hydrophilic. So hydrophobic is what I like to think about first, because I know it's got hydro, so that's water, and phobic means water fearing. I can remember this because hydrophobia, a phobia is something you're scared of, and that means that the other option, hydrophilic, is loving, water loving. And what this really means is if something is hydrophilic, it can dissolve in water, like our sugar. If something is hydrophobic, it will not dissolve in water. So an example of this is lipids, and these are fats. And I think of this too as mentally, as think of Italian dressing, you leave it out and the fat and the water separate because they don't want to stay together. They're hydrophobic, the fat is. Triglyceride, you got 3, right? 3 molecules in here. A major portion of fatty acid is the long hydrocarbon that stores a lot of energy. So most of the fat is storing that energy. And fat has a lot more energy than carbohydrate. That's why it's so hard to lose weight, because you have to use so much of that energy, right? You just really have to use it. Okay, for body fat, the technical term is adipose. It looks like little Skittles under a microscope. It's hilarious. And we need some body fat because it cushions our vital organs and insulates us. So it helps us stay warm, and it keeps everything from bumping and knocking and hitting bones. So if we look at specific types of fat, there's 2 types that are typically talked about. That's unsaturated and saturated. Unsaturated means it has fewer than the maximum number of hydrogens. Remember, each carbon is typically surrounded by hydrogens. This means that somewhere in there there's a double bond to a carbon, so it doesn't have the maximum number of hydrogens. These are plant and fish fats typically, and at a room temperature they'll be a liquid. These are also considered healthier. Saturated fat means they do have the maximum number of hydrogens, so every carbon is completely surrounded by hydrogens, and those tend to be animals and solid at room temperature, right? So think of butter versus olive oil, right? Or lard, that's better. Think of pork lard, nice solid mass, versus olive oil, nice and liquid. This isn't always true. When I had coconut oil, often it got hard. But if it's liquid at room temperature, it tends to be healthier. And we care about all of that because we do not want that plaque buildup that leads to heart attacks and strokes, right? Now, I'm sure you've heard of trans fats. Trans fat is when they use hydrogenation to add hydrogens to an unsaturated fat. And right now, the scientific literature seems to be considering this even less healthy than a saturated fat. So, given a choice between something that's hydrogenated and something that's just saturated, pick the saturated, right? Okay, so steroids, you always hear about these with sports. These are a lipid, they're hydrophobic, so they eat the water, and what we care about is they have cholesterol and sex hormones. This is really what causes problems, because estrogen and testosterone. So if you're a guy taking a steroid, you're going to get some estrogen that your body's not usually used to. If you're a girl, you're getting that testosterone that your body isn't used to. This has caused, with people who abuse steroids, serious physical and mental issues, violent mood swings, depression, liver damage, high cholesterol, shrunken testicle, reduced sex drive, and infertility. So this made me think, though, so we don't allow steroids usage in athletes, but we do allow people who have artificial limbs that are crazy scientific to compete. Not sure if that's really fair. So now I can talk about amino acids. These are the building blocks of our proteins. In fact, let's stick proteins in here. Better. Okay. So these are the building blocks of our proteins. In your body, when we're talking about proteins, it's not just like steak is protein. Proteins do everything. They allow for different reactions to occur. They give energy. They're just going around doing like every job known to God. I just think of them as the gopher. If you're not sure what is causing something in your body to happen, it is probably a protein. They're made of amino acids. And these are very specific. You get a bunch of them. It's a peptide bond. You get a whole bunch of those. It's a polypeptide bond. We're going to talk about these more later on. But that is our basic. So protein, amino acids. Now, stuff can happen that's not good. And that's mutations. And this can lead to a small change, like say we change the word tasty to nasty, but can have huge issues. And they have an example of sickle cell. If you're a sickle cell carrier, that means your blood cell is slightly different shaped. Now this keeps you from catching malaria so much. However, if you have the sickle cell anemia, it means your blood has a hard time coagulating. So let's go down. Other ways you can cause mutation is a denaturation. This is when there's a change in temperature, pH, some other part of the environment, and the body cannot handle it. So normally, if you think about the environment, it's getting colder, warmer. We figure out ways to keep our internal organs happy, but occasionally it's too extreme and it messes up. The book gives the example of an egg white. When you're cooking it, turns from clear to opaque. You can have misfolded proteins. So they fold the wrong way, they're not able to have the reaction they need to, and this is associated with diseases like Alzheimer's, mad cow, and Parkinson. So let's look at DNA specifically. You have nucleic acids. These form DNA and RNA. These are made of nucleic acids, A, G, C, and T. So A is always going to pair with T, G is always going to pair with C. So if you have one of the two strands of DNA, you know what's on the other strand, because if you see an A, on the other strand is going to be a T. You see a C, other strand's a G. You see a G, other strand's a C. You see a T, other strand's an A. So you just need one to figure everything out, which is important when it comes to copying. And DNA, of course, is built as a double helix. It's got that twists and turns that you think of as the classic DNA. That is just one way of folding the DNA, so it could look other ways, but this is the one you're going to think about most often. Okay, I hope that helped you understand Chapter 3.